So there used to be a song. There used to be a dance song back in the 80s. Let it roll, let it roll. I don't know if you could Google it or find it. It would have been nice if I had that playing. But anyway, today we're talking about Rolle's theorem. All right? You could always go to the rolling down the river type of song. Anyway, let's talk to you about Rolle's theorem. The first thing you need for Rolle's theorem is a continuous function. That is huge because even on the AP exam, they'll give you stuff to try with Rolle's theorem, and if it's not continuous, it doesn't work. So the first thing we need for Rolle's theorem is we need a continuous function. All right? And it kind of looks like this. If I have a point here and a point here, and it's continuous, it has to have a max or a min. That's what it says. So whatever happens here, there has to be a point, because this makes a straight line. There has to be a point somewhere here that the derivative of this function is 0. That's all Rolle says. These two must be equal, and this line must be horizontal. Okay? A lot of times they ask you to look, you'll see some problems in a moment where they ask you to see if it's continuous on a closed interval, differentiable, that derivative is 0. Okay? Then there's another theorem that says it's very much like Rolle's theorem. And it's called, let me give you some love here. It's called, do it a different color, green. Okay? It's called the mean value theorem. The mean value theorem, mean means average, so it's the average value theorem. And what this one says is the same thing that Rolle says, except the points is a continuous function. This has some slope, some m. Well, if it's continuous, somewhere along the way, there has to be another slope parallel to that one that has that same slope. It makes a heck of a lot of sense. All right? So somewhere these two lines, if you take the slope between those two endpoints of the function, whatever slope this is, for example, is this 6, then since it's continuous, that's huge. Somewhere along the line, there has to have a slope of 6. Just like somewhere along the line it had to have a slope of 0. That's what it means graphically, because you know I always like to tell you what it means graphically. The mean value theorem and Rolle's theorem are done with the alternative form of the derivative. And let me remind you, remember the alternative form of the derivative, f of c is equal to f of b minus f of a all over b minus a. That's the derivative at some c. Okay? Hopefully you remember that, but remember this is, everybody was asking me, when are we going to use this? When are we going to use this? Now we're going to use it. So let's do a couple of problems so you get the gist of how it goes. Okay. We have Rolle's theorem. Find all values of c in the interval such that, remember that's such that, the derivative is 0. And it gives you a function, and it gives you an interval. So all of these will have an interval because every single one has, remember when I did all those two graphical examples, they have endpoints. It's not an open interval, it's always a closed interval. So the first thing we have to do is check out if this thing is continuous and differentiable. So is this differentiable? Absolutely. There's nothing that's going to give me any undefined action or something. All right? So differentiable means continuous. So this guy is differentiable. It's the first thing you got to check. Because on one of the tests, maybe it was 2 years ago, it's differentiable. Because this is just a cubic. All right? It's an x times an x squared. All right? And now I'm going to check the endpoints. You have to make sure the endpoints are equal. All right? So with Rolle's theorem, remember they have to be equal so that line, that horizontal line goes through it. So let me check f of -1. Just plug it into the function. I get -4 times 0, so I get 0. And now let's check f of 3. I better get 0. And I do. So the endpoints match. Endpoints are equal. We are ready to do rolls. If one of these guys failed, no Rolle's theorem. Can't do it. So we need a differentiable, and you need the endpoints to be the same. So now watch the math. All right? The first thing we're going to do is we're going to take the function and expand it. It expands after you FOIL and all that happy stuff. It becomes x cubed minus x squared minus 5x minus 3. Take the derivative. All right? So after you check these two, it is important to check them. FOIL, multiply, and then we're going to get f prime equals, well, we can take derivative of this, 3x squared minus 2x minus 5, okay? And we're going to set that equal to 0. And then we're going to find the c, or the x, that makes the derivative 0. We want to know when the derivative is 0, because these 2 points are here, that line, okay, the 2 endpoints are 0. So we need to find when the derivative is equal to 0, that same one. So set this guy equal to 0. We'll factor nice. You got this. The factoring is no problem. 3x minus 5, x plus 1, all right, equals 0. And we get this c to be 5/3, or x, if you will, and this c to be -1. Well, let's remember back up here. Keep coming. There's our interval, -1, 3. So this, oh wow, did I screw up? -1, 3. Well, -1, I don't know why I wrote is not in the interval. I believe it has to be between the endpoints. If it's the endpoint itself, it doesn't count. Because remember, I have 2 endpoints, and I'm looking for 1 point in between that gives me that same slope. I found it, 5/3. And that's what the problem asks. If we look back up here, find all values of c in the interval where the derivative is 0. Okay? In the interval. Has to be within the whole interval, not counting the endpoints. Important. Between the endpoints. All right? Don't count them. So let's do another one. Mean value theorem or rolls, doesn't matter. Okay, you'll see the difference between them. So I look at this guy. From 1 to 4, is this guy differentiable? It seems like it, because if I think of the graph, it's like a 1 over x graph or a hyperbola. And the hyperbola is only at 0, we got problems. So we're between 1 and 4, so we should be good. All right, so differentiable. Not using Rolle's theorem. I don't know why that was there. That was me not doing something. So for the mean value theorem, it's a little bit different. We're using that alternate form of the derivative. Okay? I wonder if it would work if we didn't. We could check that out in class or something. But I'm going to use that alternate form. So I'm going to get f of 1 minus f of 4. And I'm going to put it over 1 minus 4. So I'm going to get this guy equal to 1. That is the derivative. Okay? And I think you would know, because here's the deal. All right? Check this out. If I plugged in f of 1, and I tried to do it like Rolle's theorem, I would get 1. But if I plug in 4, I get 4. These guys aren't equal. The endpoints aren't equal, so go to the alternate form of the derivative. So I now know what the derivative is for that point. It's 1. So I'm going to take, so this is okay. Mean value theorem, okay. All right, so now we're going to say I care about it being 1, not 0 now. So what I'm going to do is take the derivative equals 4x squared. And here, in slow motion, 4x to the -1 When I take the derivative, becomes that. I think you got it. Now, I want to find out when this guy is 1 now. Set it equal to 1, not 0, because we want these guys to be the same. So, when is this guy 1? When x is 2 and negative 2. So the answer is when x is 2 or negative 2. Oh, negative 2, not in our interval. This guy's not in the interval, because if you remember, the interval is 1 to 4. So x equals 2 is the one we're looking for. Cool? Hope you're good so far. It's really not that bad. So I got a little story for you. And this goes to Eric Lands. This is an Eric Lands problem right here. So I got a story for you. So here I am. Okay? I'm driving along the parkway, and I go 5 miles. I see a cop, okay? And let's say I'm going this way, okay?
Can I have your attention, please? Any student not involved in an extracurricular activity must leave the building. Again, any student not involved in an extracurricular activity, please leave the building. Thank you.
So I pass this cop right here, and I'm doing 55 miles an hour. Fine, I'm on the parkway, right? 55 is good. So I'm chugging along here, and I pass this cop 4 minutes later, and I'm doing 50 miles an hour, and guess what? I get pulled over, and the cop gives me a ticket. And I said, that's impossible. And he says, no, it's not. And this is what he does. He says, first of all, these are miles per hour. This is minutes. So actually 4 minutes is 1/15 of an hour. Okay? And they're going to use the mean value theorem. Any cop that comes up and uses the mean value theorem, holy cow, you're done. And he goes like this. He says, your distance, okay, the distances that you went were 1/15, and I took you at distance, and the time was 0. This is 1/15 minus 0. So I say, okay, how far did I go in this time, 1/15? I went 5 miles. This was 0 miles. This is 1/15. This is 0. And then this is miles. This is hours down here. So he says, okay, you were doing an average speed of 75 miles per hour. You now have a nice fat ticket. Average speed. Mean average. Getting the average speed. This is taking the derivative, okay, putting the time in, okay. If this distance of this gives the distance at 1/15 gives you the 5 miles, okay. This is the time. So distance over time is speed, okay. 75 miles per hour, I get a ticket. Am I happy? No, nobody's happy. But remember, millions of peaches. Peaches for me. All right, anyway, that's been my anthem for the last couple of days. I got some homework for you to do in the book. All right, it's in the book. I apologize, but this is what it's going to be. It's page 176. This looks like a lot. Let's see if we can calm it down a little bit. Let's do 12, 15, 16. And I'm going to tell you a little early. Look at 15 and 16. Make sure that you could do rolls. Hint, hint. 22 is a nice trig problem. Okay, Sydney, talking to you here. All right, you're my trig expert. And we'll do 26. And yeah, I like these problems. 41 to 44 looks a little redundant. You know what? I'm just going to say, look at 44, look at 48. Those two, they may not satisfy, so you may not have to do anything. Wink, wink. And number 54. 54 you'll like a lot. Okay? That's your homework that goes along with this video. I expect you to do it in class. I'll have 4 problems for you on a worksheet. It'll say quiz, but it won't be a quiz. You know what I said. And